Hello everyone, we will continue with the course evaluation of textile material. In last 2 weeks what we have discussed is that the population, sample and how to draw the sample we have discussed, and also we have seen that different types of material or materials in different form is to be sampled in different way. Also we have discussed about practical statistics, like how to do significance testing, what are the implications of this significance testing in taking decision. Now, today we are going to start the actual evaluation of textile material. What we will discuss, we are actually, it has been divided into 3 distinct categories, because textile materials are mainly in 3 forms. First, it is a loose fiber form, second continuous yarn form, and third it is a fabric form. So, overall the planning is that we will try to first finish the characteristics of fiber, then we will discuss yarn, and finally we will discuss the characteristics of fabrics. So, today we will start the evaluation of one of the most important characteristics of fiber, which is length. Length of fiber, particularly for man-made fiber, it is not that important. For natural fiber, except say silk, for rest other fibers are basically it is a discontinuous in nature. So, we must try to see how to measure the fiber length, and majority of the fibers, textile fibers for apparel use or natural fiber we are talking about is cotton and wool. So, our focus will be here to measure the length of cotton and wool. So, first let us see why to measure the fiber length. First is that quality assessment. So, quality of a fiber is dependent on various parameters. For example, fiber length, how long the fiber is, its diameter, its strength. So, length is one of the parameters which is important to be measured. Okay. So, for quality assessment of any fiber, so we have to first measure the length, particularly staple fiber. Then quality prediction. So, quality prediction here, that means quality of the final product. So, quality prediction here, the final product is either in the form of yarn or in the form of fabric. So, longer fiber will have higher contact area. So, we can have better yarn strength. So, to have higher yarn strength, we need longer fiber. So, our idea is to know by testing the fiber length how long the fiber is, and if the length is less than the prescribed length, we may straightway reject that fiber. Okay. And also long fiber will have better processability in spinning. So, fibers with short fiber, higher quantity of short fiber, higher proportion of short fiber creates problem. There are various characteristics which are directly related with the fiber length. These are strength, evenness, and even for longer fiber we can play with the amount of twist. So, for if we use the longer fiber, we can have lower twist. So, lower the twist, the appearance of yarn and fabric will be much better. So, it will enhance the luster of fabric. Okay. So, directly we can predict from the length value what will be the ultimate quality or characteristics of the final product. Next importance is that fiber breakage study. So, we may like to know that whether a particular machine like blow room, carding or any other machine, combing or any other machine. So, due to the setting, problematic setting, so fiber may get damaged. So, fiber may break. So, to study the breakage of fiber, what we have to do? We have to first measure the length. So, we measure the length before processing and also after processing, and if we compare that whether there is any significant change in length. So, significant reduction in length, if at all there is any significant reduction in length, we can actually reprocess the material, and also we can do proper checking of the system. So, by measuring the fiber length, we can predict the performance of the particular process. Also, machine setting depends on the fiber length. So, depending on the long fiber length, so longer fiber will need longer setting. So, for machine setting, its fiber length data is extremely important. Next is that combing efficiency. So, in combing, what our idea is to remove the short fiber. So, that how much short fiber is being removed during combing, that is the combing efficiency. So, that we can predict by measuring the fiber length, and also we can check whether any long fiber loss is there or not. So, combing's main objective is to remove the short fiber less than prescribed specified length. So, if the combing setting, combing performance is not up to the mark, then it may remove the long fiber also. So, by checking or by measuring the fiber length or fiber length distribution, we can tell that whether the combing is doing its performance perfectly or not. Okay. So, fiber length, now let us see the fiber length characteristics, length of fiber, how can we express, what are the different ways to express the fiber length, and one by one we will discuss in details. So, fiber lengths can be expressed in terms of first staple length. Okay. Staple length we will discuss in detail, it is a overall idea about the length. Okay. This is the staple length. Next is that mean length. So, fiber length we can express in terms of mean length. Next, it is upper quartile length, UQL, okay, upper quartile length. fourth one is by effective length. We can express the fiber length in terms of effective length, modal length, okay. Span length. Span length, there are different types of span lengths. So, more commonly used span lengths are 50% span length and 2.5% span length. Next is upper half mean length, and all these parameters they are important, but different measuring technique, this different measuring technique gives different type of parameters. Okay. So, these are the upper half mean length, span length, these two parameters it is given by the fibrograph. Okay. Like effective length we can measure by the Combe-Shorter diagram. So, upper quartile length, effective length, mean length we can measure by Combe-Shorter diagram. So, different methods of measurement they give different parameters. Next is that after knowing the fiber length, we would like to know the variability of fiber length. So, most of the almost all the natural fibers they are not uniform in length. So, for a fiber which is say mean length is longer, but if the variation is very high, then fiber will be rejectable. So, that performance of the fiber is actually judged by not only by the mean length or span length, it also it is judged by the variation in length. So, fiber it is very important to know the variation and length of the fiber. So, variation in length this it is expressed by first is the dispersion percentage. Dispersion percentage we can get from the Shorter diagram. Uniformity index is another way of expression of fiber length variation. Then uniformity ratio. So, uniformity index and uniformity ratio we can get from fibrogram. This details we will discuss. Short fiber content we can get from the this different types of curves and the floating fiber index. So, these are the ways from by which we can express the fiber length distribution, fiber length variation. Okay. Now, one by one we will try to understand the terms. So, staple length actually it is defined by US Department of Agriculture, USDA. It is a standard definition what they have made is the it is the normal length of typical portion of staple fiber having relative humidity of 65% and temperature of 70 degree Fahrenheit without regard to value or quality. This is the standard definition. Now, what does it mean? It means that it is a typical length, we cannot get exact value, it is a typical value. So, typically it is a we get like this in the form. So, you take some tuft, then draw and double. In this way we would like to make the fibers stand parallel. Most of the fibers we are making parallel by drawing and doubling. So, in this way and it will be typically half inch width. Okay. This is the tuft. Now, let me draw and show you. So, typical length is that. So, these are the fibers. Okay. Now, this fiber we have actually doubled repeatedly, like what we are doing, we are drafting and doubling, In this way what we will get? We will get the fiber strand like this. So, here what we will do? We are not bothered about the long fibers, these fibers we are not bothered about, the projected fibers are not the important one. Here we will try to take one point where there is a clear change in density. these are the higher density portion where majority of fibers are there, okay, and suddenly there is a change. So, we by actually experience we will get length, this is the length where the in either sides. So, at this point, so this is the point and this is point A and point B. So, up between A and B majority of fibers are there, majority of suddenly after A, if we go beyond A. So, left side of A, here we will see sudden change in density is there. So, there is a clear line is there. Similarly, in case of B, so up to B there is a density is there, more majority of fibers are there. So, beyond B there is a sudden change in density, few fibers. So, we are discarding these fibers. So, this length AB length, this is the actually staple length. Here the staple length we actually cannot use for any quality purpose. This value is used basically for only comparative quick evaluation of fiber length. So, that is why it is written without regard to value and quality. So, we would like to know the what is the overall length of the majority of the fiber. So, as per USDA, the classification of cotton fiber according to the staple length. So, staple length is judged by the experienced person, okay. And if different person does. So, if we give the fiber bundle, fiber bulk, okay, to different person, so they will land up with different results. So, it is a subjective in nature, only experienced person can do this. Okay. And as per the USDA norms, so less than 20.6 millimeter it is a short fiber, 20.6 to 25.4 it is a medium length fiber, and like that. So, above 34.9 it is a millimeter, it is a extra long fiber. So, this is the actually classification of staple length as per USDA. Okay. Next is that it is a mean length. Mean length of the fiber is defined as the it is a average length of all fibers in the test specimen based on weight length data. So, it can be weight length data or it can be number length data based on the weighing. So, based on the mass of the fiber mass for a particular length group, we can get the mean length, which is called the weight length data. So, mean length based on weight. So, ML W is the W1 L1, W2 L2, W3 L3 like that. So, if here it has the example is that though the fibers are divided into 3 length groups L1, L2, L3. So, L1 length group, that is their mass is W1, L2 length group's mass is W2, L3 length group's mass is W3. So, the mean length based on the mass weight, so that is divided by W1, W2, W3. Now, let us try to see here. Suppose this is the fiber length distribution curve. Here what we are doing, these are the fibers. So, cotton fibers are there or maybe wool fiber, and this fiber, this is the length and this is a proportion of fiber. Okay. Now, this we can have, say these fibers are length group L1, all these fibers we are dividing into say 4 length groups, this is say L2. So, this means L1 means this is upper limit, this one is lower limit and mean point. So, this is the range, okay, class limit, and L1 is the that mid value of the class. So, this is L1 group, this one L2, similarly this is say L3 length group L 3 and this is the length group say L 4 like this. Now, then what we do? We take these fibers and measure the mass of the fibers in a particular say microbalance. This is becoming W 1. Here the mass is W 2, here the mass is W 3, W 4 like this. So, that mean length based on the mass will be L 1 multiplied by W 1 plus L 2 multiplied by W 2 like this, divided by W 1 plus W 2 plus. So, this is the way we can measure the mean length based on mass. Okay. It also can be calculated based on the number. In that case, it is called number length data. Okay. So, number length data it is a simple. So, mean length based on number is that M L n L 1 plus L 2 plus L 3 so on, and then L is that number. Now, let us see once again. Suppose we have fibers, these are the fibers. Now, what we do? This is L 1, L 2, L 3, L 4, L 5, L 6, L 7, L 8. So, say these are the L 8 fibers. So, you want to know mean length. So, it is very simple, you just add and then divide by the number of fiber. So, this is L 1 plus L 2 plus L 8 divided by 8. So, this is the mean length divided by Western length. So, we must clearly understand the difference between mass based length and number based length. So, these terms are widely used in the industry, both in cotton industry, particularly in woolen industry, the mass based data and number based data. Next term is that upper quartile length. So, as per ASTM, the upper quartile length is defined as the fiber length which is exceeded by 25% by weight in the test specimen. That is the upper quartile length. Now, again let us discuss the upper quartile length based on say mass. So, again this is the fiber length distribution, so length, and this is the proportion of fiber. Okay. Now, here this mass has got say x mass total. If we take the total fiber, the mass of the total fiber is say x milligram, x unit. Now, then we will keep on taking the from the starting from right side, we will keep on weighing this. So, what is that? It is a top 20%, 25%. Okay. So, that is why till it has become say 75%. Suppose at this point this is the weight is 0.75 x mass. So, that from there this point, so this is the 25% weight, this is 25% weight mass. If we talk about the mass, this is total mass is 75%. So, this length is called upper quartile length. So, that as per definition, the upper quartile length is defined as the fiber length which exceeded by 25% of fibers by weight. So, that means that particular length is exceeded. So, rest 25% fibers will be more than that length. That is called upper quartile length, and based on that it has been classified again. So, upper quartile length we can see less than 27.9 is the short fiber, 27.9 to 31.5 it is a medium fiber. This actual classification is as per ASTM classification, but this may not be true for all the fibers. Like some short staple fiber, we cannot use this type of characteristics, this type of classification, because in short staple fiber 27.9 millimeter may be the longest fiber. So, that way this is for a particular type of fiber. Next is the effective length. So, the effective length is the longer than the average length, it is longer than the average length, and is the measure of the length of the majority of long fiber in the sample. So, here in this picture this is the Schottard diagram. In this Schottard diagram we will discuss details of the Schottard diagram, but here let us try to understand the effective length here. It is L dash is the length, okay. L dash is the length which is called effective length. Now, here it is a longer than mean length, mean length will be somewhere here, if we measure mean length will be somewhere here. So, effective length is longer than the average length of the fiber and is a measure of the length of the majority of the long fiber here. So, majority of the long fiber here it is the effective length. The effective length is described statistically by the upper quartile of the fiber length distribution obtained by ignoring the short fiber. Now, this is we have to understand here. So, this is the length described statistically by the upper quartile of the length distribution. This is the length distribution obtained by ignoring the short fibers whose length is less than half of the effective length. Now, this is the effective length, suppose this is a midpoint. So, the half of the effective length is this one. So, if we remove this length, this R B, this portion if we remove, that means remaining fibers will be this one O R. So, O R if we divide into 4 equal terms, then this O L is the upper quartile, upper quartile. So, you divide O L, then another 1/4, then 1/4 and up to O R. Okay. So, this O R we are dividing into 4 terms. So, that this 1/4 top 1/4 that distance L1 L2, that is called upper quartile of this upper quartile of the fiber length distribution, this is called effective length. So, detail we will discuss, and this effective length is mainly used for roller setting, okay, because it is basically it shows the longer higher portion of the fiber length. Next comes the modal length. Modal length is the length of the fiber with higher frequency, that means majority of the fiber lengths are in that zone. So, if we take the distribution here, so suppose this fiber particularly at this length, the frequency is, this is the frequency, this is the proportion of the fiber. Now, next is that this is the proportion, okay, and like that the proportion is actually given here, okay, at the horizontal line. Now, we have to see here which portion has got the width of the rectangle is highest. So, here this the rectangle of this portion, the width is highest. So, that length, height of that portion, that rectangle will be termed as the modal length, which means the majority of the higher frequency of the fiber length is in that range. Okay. The modal length of long staple cotton is higher than the mean length. So, it will get shifted to the higher direction due to the progressive increase in the skewness with the increase in staple length of the fiber. So, with the it will be skewed towards the higher length, because the if we are talking about the long staple cotton, the majority of the long fiber will be on the longer side. Okay. So, that majority of the fibers, so that is why modal length will be higher. So, from modal length we can get overall idea, rough idea about the length distribution. Next comes the term span length. The span length is the length of the fiber at a distance spanned by a specific percent of fiber, or it can be by mass, okay, by number or by mass in the test beard, considering the remaining considering the reading as 100% at the starting point of the scanning. Now, let us try to understand here. Now, suppose we have prepared a fiber clamp, this is the clamp, okay, and it is typically used in fibrograph, fibro sampler. Now, this clamp is clamping the fiber, and this is the type of way, type of distribution. So, all the fibers they are starting from the this point, clamping point. Okay. Now we like to scan the fiber from this point. This is the starting point close to the this clamp, okay, point A. This is the point A. So, at this point, at the end point here, the number of fibers say 100. Suppose at this point number of fiber is say 100, let us say. Now, we try to count the number of fibers here. At this point number of fiber is 100, then we try to move from this point a line AB, line AB we try to move rightward away from the clamp. Suppose at this point, at point say C, again we are trying to count the number of fiber. Here we have count, say this is 100. Suppose at this point, suppose we are counting the fiber at say it is a say 80. So, this is O at is the starting point, at C point it is 80. So, after again further moving, suppose at this point at D we have count the number here, this number is suppose it is a 50. Initially there is 100 fibers, now it is 50. Now, this distance OD is known as 50% span length. This is the distance OD is the 50% span length, that means 50% of the total fibers are longer than this length, that is why 50% fiber length OD is the 50% span length. Now, we again go further gradually, and we have reached suppose a point where it is a E point. So, at distance OE, so at the point E we found that only say 2.5% of fibers are there, 2.5% of fibers are there. So, here this distance OE is called 2.5% span length. So, that is why this is the distance, that one should be careful here, higher percent means the lower in span length. So, 50% span length means it is lower in value than 2.5% span length. Okay. So, that the distribution of fiber length, it gives idea about the total distribution of the fiber length, and so the span length is the length of the fibers at a distance spanned by a specific percent of fiber. It can be by number or it can be by weight. By weight also we can do. Okay. In the test beard, considering the reading as 100% at the starting point of scanning. Okay. So, it is the most common span lengths are commercially used are that 2.5% span length and 50% span length. Now, as we have already discussed, we have seen. So, this is the type of curve we get. Okay. This is the fibrogram. Okay. Now, try to see this is the fibrogram how to form. Initially say 100% fiber here. Now, we have started scanning it, normally it is optically scanned, the density or number of fibers we can calculate. So, as it is moving here at this point it is a 50% of that fibers are there. This is called 50% span length. So, it is moving further, okay, and number of fiber as it is moving further. So, number percent of fiber is reducing gradually. So, length is length from the starting point, the clamping point is actually increasing. So, number of fibers is reducing, it is 20%, then it is 10%, 5%, almost 5%, and it is also reducing. So, gradually it is reducing to say 3%, and almost it has reached to say 2.5%, it is reaching. So, that is the way this is the 2.5% point here we have reached, and after that it is going, and then ultimately it will be 0. So, this length is 2.5% fiber. So, if there are 1000 fibers, so that means 25 fibers will be there more than that length. So, that is why it is called the 2.5% span length. Okay. So, in this way we can measure the span length, and based on this fibrogram we can do lots of calculation, other information we will get. So, that we will discuss gradually. So, 25% span length is defined as the length of fiber at which only 2.5% span length. So, only 2.5% of long fibers are excluded. So, rest 97.5 fibers are below that length. Okay. It provides the reference length for roller setting. Okay. So, we can set the roller based on 2.5% fiber length, because it is a majority of the length, only 2.5% fibers are there which are actually longer, and that may get damaged. So, we may this is the reference point, if we feel we can set the length a little bit above that 2.5% length, but that is the reference length to be adjusted, so that few or if any fibers are broken. So, our idea here is to that okay. So, only 2.5 fibers may break if it is there, okay, and 2.5% span length is close to upper half mean length. It is total very close to, if we do the measure the upper half mean length for long staple fiber, this is very close. Okay, upper half mean length we will discuss, and the 50% span length is more valuable as the potential measure of yarn quality and fiber spinning performance. So, 50% span length is used for to know the overall fiber length, okay, and spinning performance, and 2.5% span length is basically used for roller setting. It is a longer fiber. So, if we know that 2.5%, then we cannot say this fiber is longer, it is not that. So, if we want to know the average overall idea about the fiber length, we have to use only 50% span length. 2.5%, suppose majority of the fibers are short, okay, but few fibers are long, that will give a wrong impression. Okay. So, that is why to know the fiber length characteristics, overall length, we do not use 2.5%, we use only 50% span length. Okay. 2.5% span length only used for setting of yarn, setting of machine, drafting roller setting or different machine setting, so that less fibers are broken. Okay. Now, Now, what we have discussed that it also gives the idea about the 50% span length and 2.5%, also it gives the idea of mean length and upper hub mean length. Okay. So, and from mean length, upper hub mean length, we can get the idea of dispersion of fiber characteristics, fiber length. Now, let us see, we can see very carefully here. Now, this is the fibrogram, and the how the fibrogram is generated, that we have seen. Okay. So, 50% of fibers are there, and then it is moving and fiber percent is in 20% in like that, 10%, and ultimately it will be say 2.5% is here. So, it is a 2.5% of fibers are here, and then it has it's ended. Okay. So, that is 0% here, it is touching. So, this is the 2.5%. So, after that what is there? So, what we have to do? We have to draw a tangent from 100% point of the curve. So, when once we draw the tangent from 100% point, it will actually intersect with the x axis at a point A, that means this distance OA is called mean length, which is very close to 50% span length. Okay. That is the mean length. Another tangent we can draw from 50% point on the A point, and here this is the point B, and this distance OB is called upper half mean length. Okay. So, OA is the mean length and this one is the upper half mean length, and from there we can do some calculation. Okay. So, 50% span length is L dash, okay, and 2.5% span length is L2 dash, L2 dash. Okay. So, L1 dash is the 50% span length, L2 dash is this is the 2.5% span length, and OA is mean length and OB is upper half mean length. Okay. And if we take the ratio of 50% span length, that is the L1 dash, this one, and 2.5% span length L2 dash, this ratio is known as uniformity ratio. Okay. And we can express either in fraction or in percent. So, it is normally it is expressed in percent. So, this multiplied by 100. So, typically for cotton fiber, it ranges from 40 to 50%. Okay. That is the range of uniformity ratio, and uniformity index is the, this is the, now uniformity index is the ratio of mean length, say OA is the mean length and then upper half mean length. So, OA and OB, this ratio is the ratio, this is the uniformity index, and we can again express in terms of fraction or in terms of percent by multiplying by 100, and for normal cotton it is ranging from 75 to 80%. So, 75 to 80%, this is the actually people get confused, uniformity ratio and uniformity index. Uniformity index is the ratio of mean length and upper half mean length, and uniformity ratio is the 50% span length by 2.5% span length. And if you see the value, this is actually the, it is a basically upper half mean length, the uniformity ratio is 1.8 times less than the uniformity index. That is typical, it is a typical cotton, and we can calculate that, we will see for most uniform fiber length, that is the fiber length of say cut polyester fiber. So, all the fibers are of same length, In that case, we will see the calculation, the uniformity ratio, it is typically around 51% and uniformity index is 100% for that. This we will see. Okay. Now, the fiber length variation, that fiber length variation, this part we have seen here, uniformity ratio and uniformity index. There are other parts, the dispersion percent, as I have mentioned already, the dispersion percentage we can calculate from the Combs-Shorter diagram. Okay. Where Shorter diagram we can calculate the dispersion percentage, and L dash is the effective length here. Okay. L dash is the effective upper quartile length, and M dash is the lower quartile length. Okay. So, if you divide OR into 4 terms, it will be OL, there will be midpoint, and then O that point into MP. Okay. This is the way. So, that means MR and OL they are same of length. Okay. And this is the upper quartile length, that L dash is upper quartile length, which is known as the effective length, and M dash is the lower quartile length, and the difference between upper quartile and lower quartile is known as interquartile range. So, that L dash minus M dash, which what does it mean? L dash minus M dash will be L dash n. So, L dash n L dash, which is interquartile length, that length, okay, divided by the L dash, divided by L dash is the, it is called dispersion percent. Okay. Now, let us see how, what is the importance of interquartile range. Suppose we have 2 fibers distribution. One fiber is having longer length. So, length is this is the distribution. Okay. Here say it is the same point they have started. The longest fiber is say OA. Another distribution is say O dash. Here the length longest fiber is little bit shorter, A dash. This is the distribution. Now we have to decide which, say this is 1 fiber 1 fiber 2. Now we can decide which fiber we have to take, we have to select. So, this is the longest fiber length is OA. So, OA is more than OA dash, that is perfect. So, based on the maximum length should we go for the fiber length selection. Okay. Now, here we can measure the length distribution. Okay. Now, this is the length. Okay. Here suppose this is effective length, upper quartile length. Okay. L dash, and here it says suppose it is a M dash. Now, interquartile range will be say this is units of 1, 2, 3, 4, 5 unit. Okay. This is 1, 2, 3 unit. So, this interquartile range say will be n. So, n L dash will be, so L dash minus M dash here. But here if you see L1 dash, or here it will be M1 dash. Now, here the difference is N1 minus N1 L1 dash, this N1 L1 dash is much less than N L dash, this one. So, this distance, this is the variation, this one is the variation. Now, here this, although the fiber 1 having longer length, higher maximum length, and fiber 2 has lower maximum length, but as the variation of the fiber is less, much less here. So, the performance of the fiber 2 will be much better than fiber 1. Here there will be high floating fiber, the fiber loss will be very high. Okay. So, we should go for the fiber 2 based on the dispersion percent. So, in this way we, from the Schottard diagram we can calculate the dispersion percent and we can take decision. So, dispersion percent will give idea about the running performance of yarn. Okay. Now, uniformity index, as we have already discussed, this is the ratio of the mean length to the upper half mean length, that is the uniformity index. So, this is uniformity index, mean length and upper half mean length, that we have seen. So, for very high uniformity index is, if it is more than 85%, we can tell it is a very high uniformity index, and if it is less than 77%, so it is a low. So, it ranges from typically from, this is for very good quality, but in general for cotton it is for from USDA. So, but for in general it varies from 70 to 80%. Okay. And uniformity ratio, as we have already discussed, it is the ratio of the 50% span length divided by 2.5% span length. Okay. And if you can express in terms of percent also by multiplying by 100, and this is the value. So, it is typically 40 to 50%, that is the range. Now, it is smaller value. So, uniformity ratio always we should remember it is a smaller in value than the uniformity index by a factor roughly about 1.8. So, if someone asks, oh, I have a yarn, I have a fiber of say 45% uniformity ratio, what is the expected uniformity index? So, that is if we multiply it by 1.8. So, then we will get a rough idea about the uniformity index. Okay. Now, short fiber content, and that we can get directly from the Schottard diagram. So, what is that Schottard diagram here? Short fiber. So, if these are the different lengths. Okay. This is the upper quartile length, lower quartile length, and this is the lower, and length less than anything less than half inch, the proportion of fiber, okay, that may be by mass or by number also. Normally, it is by mass. So, short fiber content is the percent by weight of fiber having length less than the half of the half of an inch. Okay. Now, short fiber content SFC percent, what we do, this is the Schottard diagram, and we know that this is the length. Okay. Now, where suppose this length is say half inch. Now, we take this length half inch length. Now, we discard this fiber, we collect this fiber, and this is the length, and then we can take the mass. So, total mass of this fiber, total diagram say W, here it is say W 1. So, then we can get the proportion percent by weight, we can take the mass, and this is the percent of the short fiber. Short fiber content, it is important in various applications. It can also be measured by in percent by number, as I have mentioned, of fiber having length less than half inch, okay, with respect with the respective short fiber content percent in number. Okay. So, that by weight or by number we can calculate, and the short fiber content of fiber is very important, particularly in combing. So, percent short fiber in cotton increases the cost of processing. Okay. Like if the short fiber content is more, so that fibers less than half inch typically we would like to remove, discard this fiber. Okay. When once we go for combing, we try to remove all the fibers less than half of inch, because these fibers will create problem of hairiness and strength related problem, and higher short fiber content means it will go for waste, and it is a economically it is not viable, it is a cost of processing increases, and more short fiber content, higher short fiber content fiber you normally do not use for carded yarn, then we have to go for combing. So, unnecessary there will be cost implication. So, for that we must know what is the short fiber content of a fiber mass. Also it contributes to weaker yarn. So, yarn strength will be less, okay, and less efficient spinning process, because the short fiber higher short fiber content will have weaker yarn. Also the yarn uniformity will be poor, because it will create the floating fibers. Okay. Long length fiber are mostly preferred due to the reduction in number of fiber ends, that is the hairs, okay, with a higher strength yarn in the same length. Okay. And floating fiber index, the floating fiber index is an alternative to short fiber content, that is that I have already mentioned. The short fiber content is the indication of floating fiber index. So, shorter the fiber, the more will be the floating fibers. So, it explains the number of short fibers which are not clamped by in between by the nib rollers. So, that the short fiber content if it is high, then it will give indication of floating fiber, and which will actually create problem. These are not gripped by the pair of drafting roller. The fibers that are floated on long fibers to pass through in the drafting zone without the influence of applied drafting mechanism. So, drafting mechanism it is not actually giving any help, like this is drafting roller, this is the front roller, this is the back roller. Okay. Now, fiber mass is getting drafted, this is moving in this direction, this is moving faster speed, this is slower speed. Okay. Now, the short fiber content, short fibers are the floating fibers are like this. This is neither gripped by the back roller nor by the front roller, it is a floating, it is moved by the surface contact of the normal fibers. So, these are the floating fiber. These floating fibers create problem of yarn uniformity. So, what we have discussed? We have discussed in detail of fiber length parameter, fiber length uniformity parameters, and now in next segment we will discuss the methods of measurement. Till then, thank you.